Selamat pagi. Dari PPSDM, apa suara saya terdengar?
Ya, terdengar Mas.
Aman ya?
Ya, aman. Aman.
Good morning, Widow. How are you? Good
Hello.
morning, everyone. How are you?
I'm very well, thank you.
Thank you all for joining. So today's moderator will be one of our team, Averus. So I think now it's 9 a.m. So 9 sharp. So I think, Faye, you could start now, please.
Thank you, Bu Ani. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, and good evening, depending on where you're from. Everyone, welcome to the Indonesian Virtual Lab Center of Excellence Regional Focus Group, April 2025, Artificial Intelligence and Satellite Meteorology for Future Forecasting. The Honorable, all speakers, and also all the participants of this meeting. I'm Averus, and I'll be the moderator of today's agenda. I'm very pleased to see you here and welcome you to this meeting. Before we begin, I would like to introduce you to the speakers. The first is Mr. Habib Rahman from Directorate for Public Weather Service of BMKG, who will presenting about utilization of deep learning or weather nowcasting. And the second is Mr. Muhammad Rian from Meteorology Al-Jufri Meteorological Station, Palu, Sulawesi Tengah, who will presenting about blending NWP, numerical weather prediction, and machine learning through 2D VAR data assimilation for rainfall prediction. And now let's continue to the main session. The presentation from speakers and will be 20 minutes each, and after that, we will continue to the Q&A session also in 20 minutes. And so let's start with the first presentation by Mr. Habib from the Directorate of Public Meteorology. Is Mr. Habib ready?
Yes, I'm ready. Thank you, Mr. Averus.
Yeah, okay. So to Mr. Habib, you may begin.
Okay, good morning for our friends in Indonesia and good afternoon for our friends in Australia. First thing first, can anyone hear my voice clearly?
Yes.
Okay, let me continue to my presentation. It's about the utilization of the deep learning for the nowcasting. Let me share my presentation first. Right now, everyone can see my screen.
Yep.
Okay.
Can see that.
Okay. So, in public meteorology in BMKG, we developed in nowcasting algorithm like using the statistical and using the AI or using the deep learnings. First thing I want to talk about the existing model and how we make a nowcasting. To make a good nowcast, we must predict this the matter stage of the thunderstorms and its propagations. For the propagations, we have some statistical method and using the PySteps library. First is about the extrapolations in SPROG. It's developed by our team in radar team. It's using the I think it's about the radar DBZ or reflectivity. And as you can see in the screens, there are three algorithm is nowcasting with using the N-file auto-regression nowcasting using N-fill, and you can see some results are quite different. But let me continue again about the steps nowcast. In our production right now, in our prediction right now, we have the product of the steps, short-term sample prediction systems. It's using the statistical method for predicting the next frames of the first initial radar. As you can see in the left is the steps algorithm and the right is the lambda. And for this deterministic nowcast, we're using the Himawari using the SPRG. We use this rainfall converting from the reflectivity from satellite, and we make the propagation of its prediction. You can see this result is I think is quite satisfying when we can see the future of the propagation of the rainfall, like in the South Sumatra. It's quite good. And for the machine learning, we're developing the convolutional neural network using the LSTM for the predicting the spatio-temporal. The result is quite satisfied too, but there are another algorithm for the AI. But first thing first, I'm gonna talk about the how we can identify the storms. We're using some algorithm like the overlay, CHIMEX, the storm structure analysis. It's a product from the Rainbow 5, and it can predicting or detecting the presence of the storm cells using storm structure character. The products produce the maximum height of the cloud, the minimum height of cloud, maximum of the reflectivity, and the black color is where the storms, the identifications, the initial of the storms, I mean, and the pros of this algorithm is quickly identify storm cells, understand storm structure and characteristic, but the pros is if the data is incomplete, it cannot be generated intensification or structural analysis for the thunderstorm. Another of the initiation prediction for nowcast, or I think the identification of the thunderstorms, we're using the ChIMAX Titan thunderstorm identification tracking analysis and nowcasting. Titan is algorithm developed by NCR, and it's, you can see in the picture left, the black color is the current storms, and the next forecast is for the next 30 minutes and 60 minutes. The results is showing not only the storms intensification, but is showing also the storm speed, direction, and another like the cell top, cell volume, and mean area. And this is one another convective initiation algorithm that we're trying to develop in BMKG. This is the algorithm that developed by Meteo France, and it's using some satellites like Himawari and another. It can predict about the next 30 minutes or 60 minutes. The initiation of convective is a good first steps for making nowcast, because for making nowcast, we need to make a forecast of the initiation of the cloud, and then if the cloud become maturing, so we need to predict its propagation. This is the blending NWP. Some our algorithm like the pi steps, SPRG, and another. We need the physics approaches like using the NWP and blending to our nowcast to make the prediction good. But in this case, it's not finished yet, because as you can see, the left picture is NWP. This NWP not giving much information because it's interpolated from the global and the global model. And in next steps, we're gonna trying to make the blending NWP with the higher resolution of NWP, and we expect it to have better results. And for the AI use case for the our nowcast, we have some existing model, which is the best line is our Pret RNN. We're using this from Pepper and another nowcastnet and nownet. For the Pret RNN, it's only predicting the spatiotemporal of the thunderstorms and the rainfall intensity. And our pattern, how it works, we first train the model until it's become a confluent when the error are not much larger, or not the peak and the hill of the error is not become larger. The difference between peak and hill is not becoming larger, or it's become a convection, I think. Sorry. And we're trying to using the 80,000 epochs with the 1 year data from BMKG data satellite. And this model uses the first 10 input frames to predict the next 10 frames. If I have data from the 410 to 540, it will predict the another 100 minutes ahead, which is from the, in this case, is using prediction from the 550 to 720. And we're gonna see the next in the use case for the clearance. This is the use case. I'm using the use case in the Java area, in the West Java, because in the West Java usually thunderstorm occurring in afternoon, usually in the south area because it has a mountain area. And as you can see, the result of the prediction, if I'm using the data from the 410 to 540, does not show a strong high rainfall signal at the target prediction, which is it's 720, and the accuracy is decreases as the prediction duration increases. However, the rainfall distribution pattern and intensity change are still well predicted. What I mean is, as you can see in the left and the right picture, the left is the real case and right is the predictive frame. In the predictive frame, some part in Java are predicted well, like in Banten, this is Banten, and some part like in West Java or in Cianjur or Tasikmalaya, I think is not well prediction. If we have prediction from the last 10 frames, which means is too far from the rainfall signal at 720. And then we move the next frames. We try to making a prediction closer to target by using the input of 550 to 630 to predict the 640. And the prediction are quite improved. And the model successfully captured the heavy rainfall even in West Java and in Banten, although the special result is still coarse. And this is our model in the productions, and some model are already been deployed in our server. This is the case of in left is using the satellite data and the right is using the radar data. There are some difference from using the satellite and using the radar, because we know if we predicting thunderstorm using the satellite, yes, predicting from the top of atmosphere. When we predicting from the top of atmosphere, it's usually predicting the end file, which means it's become larger in the west area, but in reality maybe not that high, because it's predicting the end file too. And this is the real case with against the predictions. The left is the real case when thunderstorm occurring in Bekasi, and the right is the prediction. The prediction is quite good. As I mentioned, there's a prediction of end file where this area in Banten is, I think, is too large, because it's also predicting the end file of the thunderstorm. As you can see, as I mentioned before, that we have three models. First is the pre-terrain for our baseline, because the pre-terrain only predicting its spatio-temporal, not predicting using the physics approach. We're trying to find another model which suit for our case in Indonesia. First, there is another candidate which now casted from the paper. It's using two different approaches. First is the statistical using the spatio-temporal prediction, and evolution prediction using the physics process. And the prediction is quite good if we compare to the pre-RN, but it's still in the early stage for to say it's a good or not, because we're still developing this model. And another model is NowNet. NowNet is AI model though, using the satellite data. We have working together with the University of Leeds. It's for predicting the probability and initiation of the rainfall and intensification. Okay. Is my screen clear right now?
Yes,
I think
it's
it's fine.
Yes, yes.
Okay. Let me continue.
Sorry, Habib, the previous one, sorry for interrupting. If you go back to the previous one slide, please. It looks like that, no, the one after. That looks a bit like maybe Kalimantan, but just by the distribution of the reflectivity, but I can't actually see the coastline. Is that intentional?
Okay, I'm sorry. To be honest, this is not in Kalimantan. We're using the dataset from the paper. It's in United States, but
All right.
yeah, because I'm not making the plot for our regions and not using our data. I'm just using the providing from the paper, but it's still in early stage. But hope in the
Thank
next
you.
we can apply. Yeah, can apply to Indonesia. Okay, thank you. And this is the matrices from the paper. From the paper said that this is the root mean squared error. The pi steps and blending pi steps using the blending NVP itself is the higher RMSA, or is the least good one. I'm sorry, I don't know how to say it, but I think it's the least good one. And the best one is this pre-training and multi-source. What it means is another model that I forget to mention in this presentation. It's now cast former, which means it's not only using the only radar or satellite using another atmospheric parameter like the upper air and anything else that I'm forgetting about to put in this slide because we're still developing too. Another thing also that I mentioned, the Fred RNN, the prediction is quite good compared to the non deep learning like the PySteps, but because it's only using the spatial temporal prediction, not considering the atmospheric, and we think it's not really good enough. We're trying to find another approach, and this is for PySteps and LDCs. LDCs is not in this PPT. I'm sorry, it's not included. This is for NoCastNet. The NoCastNet predictions for the critical score index GSI is quite good enough compared to the PySteps and PredRNN. And the predictions, as you can see, like it seems like in the PredRNN when the predictions are become longer, its prediction become decreasing the accuracy. And in the next steps, we're trying to make this forecast from AI model into our map web server or WebGIS, sorry, for WebGIS. And this is the spread NN we're trying to develop, and some model already have been deployed. I think that's all from me. I'm sorry if I'm too fast or something is missing, but you can ask me a question. Thank you.
Okay. Thank you, Mr. Habib, for the great presentation. Now, let's move into the second speaker, Mr. Rian.
Oh, okay. Sorry.
Okay, we're gonna have question and answer session after all the speakers presenting.
Yeah, thank you.
Okay. So, Mr. Rian, turn here.
Okay, is my voice clear?
Yeah, your voice is clear.
Okay, I
Clear,
will
Rian.
share the
Time is
screen.
yours.
Can you see my screen?
Yes, we can see that.
Okay. I will this. Okay. Thank you for the chance. Now I want to present my presentation is blending NWP and machine learning to 2D far data simulation for rainfall prediction. Actually, this is the continuation of my last presentation in the same forum, I think. In my last presentation, I present about using a neural operator for rainfall prediction. And this is the advancement of that experiment. And actually, like I said before, this is just my mini experiment. So yeah, it's just fun experiment. And also you can find me in Medium, in genomexyzmedium.com or in YouTube, genomexyz video. Okay, I want to briefly show you my last presentation so we can connect to this experiment. So actually, in my last presentation, I try to predict so actually I am using GSMap data, and I try to predict from this rainfall history stack. I think it's a 6 stack. So rainfall GSMap data that I am using is 1 hour. So my feature is 6 hour, and then I try to predict 3 days. I try to find the limit of the AI model. And as I said before in that presentation, yeah, sorry. Oh, okay, I think it's just a noise. So I said in that presentation that because the feature is just the rainfall history stack like this, that's why we can only expect to catch a glimpse of the rainfall development pattern. We can expect it to predict the accurate rainfall. And this is the prediction. This is my this is the result of my experiment in last presentation. So this is the global rainfall actually from the GS map. And as you can see here, there is many false alarm here. The area of the rainfall is exaggerated in the FNO model, in the output of the FNO model. And this is the local prediction for my neural operator model. And actually, I even don't put it in my last presentation because the prediction is so bad like this. Look, there's no pattern in here. That's why I make some advancement for this experiment. I integrate the GS map data with the numeric models. And the numeric model that I choose for my experiment in here is RFG model. Now, actually, this is the question that always pop up in my mind in my bachelor days. Why not just plug the ground truth data to the model? Like it's the truth data, right? The data that we make it's the ground truth data. Why just plug it directly to the model? And the answer is actually this is the separated experiment. Yeah, this is just for the wind movement. So in this experiment, I try to plug I try to insert the observation data to this wind movement. And then for the right side, this is the proper prediction, and this is the result of the hard insert. And the result, as you can see here, there is a fast movement like this. It's like there is a storm in here, but actually there should be not any storm. So that's why this is the reason why we just plug the ground truth data directly to the model. We need to uh, we need to use the assimilation algorithm like this. For example, this is the 2D far equation, and in this equation we have the sigma. It's a degree of freedom for the observation. In here, it's for the ops and the model data, or the B here, or the background. So the bigger the sigma value in here, the bigger the tolerance of the assimilation algorithm. So in here, we try to make the G value in here to be closer to 0. And for the H in here, it's just the observation operator. What the meaning of the observation operator? It's just to make the observation data we just need to make the observation data dimension matching with the model data. Either we try to, for example, we try to interpolate them or make the model data match with the observation data. So we can do the arithmetic like this. In case if anyone curious with my function, this is what I use. And in here, I'm using the Newton method to solve the cost function. And actually, I never tried that, and I also don't know if this work or not. Actually, you can use a kinetic algorithm or particle swirl optimization to minimize this cost function. But I think this is many people using this Newton method. And this is my assimilation result. And as you can see here, for the RPG model, I think RPG model is quite good in their prediction, because for the model and observation, there's no, the pattern is quite same. And this is the assimilation result. This is another comparison, but in here I show you the difference between model and the assimilation result. And this is the feature data that I'm using. Actually, I retrieve the data, the model data in here from the Inasiam server because I have some access in the server. So I just play with this data, and because there is limited resource in my hardware, so that's why in here I'm just using several days data. I think it's until from day 1 to day 16, and this is my hardware spec. It just a standard NVIDIA. It just 12 gigabyte in its memory. So that's why, that's why I said this is just my fun and mini experiment. This is the model fast that I'm using. Yeah, it's just two level. Actually, I want to edit to like 500, 700, 850, and then 1000 level, and then add the another variable, but yeah, my limited resource. And then now the result. Here, this is the error convergence. As you can see here, I just do until epoch 20 because my limited resource and my limited data. And as you can see here, I think it's normal. There is no something suspicious in this. Everything all right. And this is my prediction versus ground truth, my result. So actually in this experiment, I'm using two modes, prognosis mode and full AI mode. For the prognosis mode, there will be some mix in the rollout of the model. There is some mix between the NWP and the AI, and I think the result for the pattern, it's quite overall. It's good. It's good because as I already show you that the data is only 16 days. And in here, I'm using, in this experiment, I think it's until 11 time step. And for the record, the per time step is 3-hour rainfall. So 11 times 3, it will be 33 hours time step ahead. Eh, yeah, 33 hours ahead. And this is for the full AI mode. And as you can see here, the result is not that good. And the thing that I catch the pattern from my previous experiment and in this experiment is if in the full AI model there is something artifact like this. Here there is something like this. There is like artifact from the last round of the prediction. That's why in my conclusion here, I might add some additional loss function to check the validity of the prediction field for the future experiment. So how it works? It works like if you know about generative adversarial network in that AI model, they have additional network to so this network just to check the result of the real neural network to check if the field is valid or not. So that's why in here I will try to using approach like that, but instead of that, I using the milder approach. I will just using an additional loss function, but it will involve some governing equation like in the Navier-Stokes. Yeah. So sorry, I just jump out to my conclusion because it related to this experiment. So yeah, in my conclusion is prognosis mode works well overall, and for the full AI mode, yeah, I saw some weird characteristic in the rollout mode. So it's like a persistent artifact from the past round. Yeah, I think it's like that. And also in the full AI mode, I saw something like there is some unnatural movement. Like if we wait. Wait, looks like I forgot to add the GIF in my presentation, but like in this example, in the real numerical model, the movement is smooth like this. So it's moved like clear like this, but usually in the AI model, from many models that I saw in the past when I saw the result, their movement, yeah, their prediction might accurate, but if we like replay the prediction, its movement will it's not there will be yeah, there will be a rare smooth movement like this. Usually they will just expand or shrink or expand, something like that. So that's why in my future experiment, I will try to make my AI model to move smooth like the real numerical model. And yeah, I think that's all. Thank you.
Okay, thank you so much, Mr. Rian, for the great materials and attractive presentation. And all right, now we will move to a question and answer session. And for all the participants, if you want to ask a question to the speaker, please kindly use the raise hand button, or you can write your question in the chat box. Okay, anybody from the participants want to ask some question to the speakers? Okay, I think in the chat box, there's a question from Aliana Sution. Hello. This question is for Mr. Rian. What is your
Okay.
motivation to combine or assimilate AI in satellite data? We all know that the rain profile we got from satellite data is already evaluated or corrected by observations such as radar, land surface, or the analysis model data. I'm just curious about the shortfall or uncertainty you identified from BMKG's current satellite product so that you have motivation to do these research. Yes, so Mr. Rian, please.
Okay. Actually, I've already said my motivation to assimilate the satellite data with the model data. Yeah, actually, it's because in my last experiments, I just using pure satellite data, and for the record, the satellite data that I'm using is just GS map because I saw that many I saw that looks like some people using this GSMap data for the ground truth. That's why I try to make I interested to input that to my model. And as I already show you in my presentation, if I'm just using the satellite data, the result will be not that good. And even when I show you the local prediction, it really bad that I don't put it in my last presentation. So yeah, my motivation is to enhance my last experiment. And yeah, in this experiment, unfortunately, I'm not using Himawari data.
Okay, got it. Thank you.
Okay.
Okay, from the other participant, anyone want to ask? Just write it in the chat box, or you can ask directly in this meeting with your audio. Okay, so Mr. Bodo, please.
Yeah, it's very interesting sort of cutting edge presentations here on AI. It's sort of an old guy. It's keeping me, I think, young at heart listening to these presentations. Maybe a question for Mohammed first. And it's something that regarding using the GS map, and maybe just maybe rather than a question, just a comment. There are limitations in using GS map, and I was actually during the previous regional focus group meeting on the Australian VLab Centre of Excellence regional focus grouping of September. I also used GS map to try to verify AI-derived forecasts. And one of the attendees, a colleague from the USA, basically brought to my attention that GS map does have limitations. And in fact, one of our VLab presentations some time ago had a JAXA staff member, Yoshida-san, present that. And one of the things maybe just to keep in mind, and this comes straight out of the presentation, is that accuracy as GS map is generally better over the ocean than over land, and over mountainous regions, the orographic rainfall is relatively difficult to be estimated. And therefore, because Indonesia is so mountainous, it's something to be aware of. So I just want to bring that to the attention of Mohammed. And what I'll do is I'll put one of the slides into the chat box from Yoshida-san's presentation that highlights some of the limitations of GS map. Thank you.
Thank you, Bodo. And I just want to ask if you know any alternative for the GS map that I can use for my next experiment.
Yeah, it's a good question. I mean, one of the other, in this particular regional focus group meeting, the previous one that the Australian one that was in September, also used the mimic total precipitable water. But of course, that's not cloud, that's precipitable water per se, but that will often give additional information that may be missed with a GS map.
I see. Okay.
Okay, so it's any more question from the participant? Mr. Bodo, you have another question or?
Yeah, I do actually. This one's maybe a question for Habib, because I noticed you've been using the convection initiation algorithm in order to looking at the local evolution and cloud advection, and so the HIMA 09, I think it is. In terms of anticipating convection, maybe just something I want to bring to your attention, if you're not aware of it, is there is, of course, also the beta version of the Prob Severe Lightning Cast, which is that was developed by Noah and Sims, and that can be applied to Himawari data as well, and it gives the probability of lightning occurring within the next hour. So just want to bring that to your attention. Thank you.
Thank you for your information. I think I can consider your proposal, but right now I'm still in early stage, but your proposal is still good. And yeah, we'll see next in our experiment, because I'm still learning about the initiation convection. Thank you.
Thank you very much for the answer. Everyone, please don't forget to fill the attendance today's agenda in the chat box. There is a form from Zoho form. Please fill the attendance list and don't forget to fill. Okay, any more question maybe? Or we just can conclude this meeting?
I have just put in the slide from Yoshida-san, sorry for interrupting there, but for your reference. And the Yeah, thank you.
Thank you, Mr. Bodo.
Thank you, Bodo.
Okay, we still have like 19 minutes for 10 o'clock. So if anyone want to ask some question, just write in the text box, in the chat box, or just raise your hand, or just directly ask to the Mr. Habib or Mr. Rian. Okay, and maybe we can conclude this agenda. So now we have reached the end of the agenda, and thank you so much for the speakers, for Mr. Habib and Mr. Rian. Thank you, Bodo, for joining this meeting, and also all the participants here. Like Chairman Burbang said, in case I didn't see you, good afternoon, good evening, and good night. Have a good day. See you again in the next RFGs, and Assalamualaikum warahmatullahi wabarakatuh.
Okay, so sorry for one final comment. I have actually for the maybe for Mr. Habib's discussion I've had, and also for anybody else who's interested, there is a recording advertising the beta version of Prob Severe Lightning Cast and in the chat box. So thank you very much.
Thank you, Bodo. Everyone, have a great day, and see you tomorrow in the next RFGs maybe. Yes, we're gonna end this agenda.
Okay, thank you, Mas.
Thank you, Kenan.